From the trenches of motorsports and Gearhead Central, this is RealTuners Radio, your all-motor, boosted, and nitrous-fed hour of power. Now, here's your hosts, the Reverends of RPM, the Faction of Traction, John Bewley, Scott Clark, Bill Fowler, Scott Evans, Mark Dahlquist, Mike Perduto, James Short, Tom Sewell, Brian Barnhill. This is RealTuners Radio.
Good evening, everyone. Thank you for tuning in. Nice to have everybody here. Let's see. So tonight's guest obviously is a big one. Mr. Billy Godbold is here with us tonight. Hope everybody out there is doing good and staying healthy and whatnot, socially distanced. I'm just going to go ahead and bring the guests in, the host from Ring Central. Gentlemen, can you hear me okay, and how's it going?
Loud and clear, buddy.
What's up?
Wonderful.
Good.
Hey.
Good to be back.
Yes, thank you, everyone. Where is, Nagel's supposed to be on here. Did he join in? There he is. Brad's on here. Awesome. Even got Brad Nagel tonight. Our guest is so interesting, he wanted to sit in. Brad is a four-time Engine Masters Challenge champion, working for Tony Bischoff. He's worked for others like Bob Book, Proline Racing Engines, and works for himself now. Does incredibly good wiring jobs. If you need a really nice turnkey car project, let him know. Anyway, I'll turn it over to you guys. Bill, you want to introduce our guest this evening, or maybe even Mr. Bewley, whichever one of you guys want to take it away. You're both good, close with this guy.
I really thought John Bewley was the right choice.
I think so. Mr. Bewley?
Where do I start? Our guest tonight, lead of R&D at Comp Cams, Mr. Billy Godbold. In my opinion, probably the single person in this country that knows more about valve train than anybody else in our hobby / industry. One of my favorite people to collaborate with on projects and to work with and to do things with. The man that helped me set the hydraulic roller LS world record and hold the hydraulic LS world record as it stands today. I mean, what else can you say? The man knows what he's doing. How's it going, Billy?
Great, John. That was a tremendous introduction. I appreciate it. I've been very fortunate. I've been at Comp Cams for 25 years now. But, I stepped into just a wonderful place there. I had tremendous people all around me. Some of the best people in the industry, from Scooter Brothers, was, just took me under his wing. Was very, very close with Harvey Crane after he split with Crane Cams and started doing his own consulting. So, I've been blessed with some of the best friendships and having guys like John that will just try absolutely anything, that want to talk about the theory, that aren't scared to go, hey, what if we move this exhaust opening 8 degrees, and go, well, that makes a goofy looking camshaft and the exhaust to intake durations don't look right and the load separation looks weird and everything like that. Like, okay, let's run it. So it's great having, I look really good in our industry, but a lot of it is because of the company that I represent, and a tremendous amount of it is because of our customers and the great things that they do. So, I joke with the guys in my office that my job is a whole lot like a janitor, and I'm not taking anything away from custodial people. We know, especially with this virus, how important it is to have a clean environment. I don't really grind a cam myself. I don't really sell a cam myself. My job is to help everybody at Comp do their job better. And then our job at Comp is to help all our customers do their job better.
You guys do a really good job with that, Billy. It's interesting. My only, we've never actually met. This is Scott Clark. We'd never actually formally met, but I've sat in on conference calls. So I was a calibration engineer for the guys at Marshall Engines up in Kearney, Nebraska. So the Origin, Blueprint, and you helped with the cams on so many engines for those guys. And so I got to sit in on some conference calls and hear how you work and how that works. And it was a really interesting process. And it's a good way to describe your position is to help your customers succeed. And in the cases where the customers have, maybe oddball requests, to step in and kind of help engineer a solution. And you did just that. And it was really cool. And then, of course, I run into you in all these pro stock shops. All the guys talk about, oh, Billy Godbold, you got to meet this guy. So anyway, nice to have you. Thanks for joining us.
Well, it is. And so you got to see some of the wide range. We've done camshafts from everything from, like when the weed eater guys, or whatever they're called, weed whackers, or whatever you want to call that thing, and knocking into it. Those guys were really good with 2 strokes. They didn't know how to do 4 strokes, and so valve train's kind of hard. So we've consulted on everything from 2-stroke to 4-stroke conversions of small engines that you'd use in a handheld device, all the way up to ship engines. And we've even been fortunate enough to do some things for Department of Defense and things like a pump to pump oxygen to work in air as an iron lung behind the seat of a fighter jet. So just about anything that converts rotary motion into linear motion.
Got it.
So it's kind of cool.
We've got somebody with one of our unique projects here in the chat with us tonight, Darren Guttrell. You remember the V10 LS cam project that we did?
Mm-hmm.
So you guys know I'm headed there in the morning, right? I'm headed to Ardmore first thing in the morning to work on that on the dyno again. But
you gonna try it with the new intake?
Yes, sir. It's ready with the new intake.
You gonna try the truck intake?
So he's got the twin throttle body to cross ram looking thing on there now.
Yeah, that was the original intake that was on that engine that GM developed for it.
No, he's got it ready to go, and Brett Willett's bringing up a max ECU so we can do actual true odd fire 10-cylinder coil per cylinder. Nice. The goofy firing order thing, which thankfully Billy sorted that out for us. He didn't even realize it. I got his notes from Darren. But that project is awesome. And once we figured out that we had the firing order wrong, it was so funny to hear that thing start up and run perfect. It's not even fire. Stupid Engine Labs article, I read that it said it was even fire, so I had it set up for even fire a couple of tries, and woo, even fire on an odd fire leads to some interesting pops and bangs, let me tell you. But
yeah, I imagine that's pretty ugly.
Yeah, but it was so smooth running once we got that sorted out and everybody knew it was right. Oh, that sounds right. But yeah, that one's coming up. Go ahead, Bewley. I didn't mean to interrupt you.
No, Darren put a comment up in the Facebook chat, and he was talking about all the unique projects and stuff that he had worked on, and it reminded me of the V10 project we all worked on.
Well, Billy's day goes like this. Billy, this is Mark Dahlquist calling from Fargo, North Dakota. I'm building a Pontiac engine, and I'm going to put 2.1-to-1 rockers on it. I'd like as close to 900 lift as I can get, but only with 240 degrees of duration. Is that something you can do? Billy's like, yeah, I think I got something on the shelf.
You have to be afraid on things like that. One time, Kenny Duttwire called up and he wanted something kind of nuts. And, he asked if I could make a camshaft that was like under 240 duration and over 1-inch lift. And I was just like, sure, I can make that. Just because you can make something doesn't mean you should make something. Right. That car was the fastest he'd ever been to the, he didn't make it all the way to the 8th mile fast, but best short times he ever had. But it was down 2 cylinders by the 8th, and it was down all 8 intake valves. And like Elvis had left the building before the course.
Yeah, just thinking about doing the velocity calculations on the intake valve with that kind of duration and lift, you're like, what's the jerk value on that?
I think it was 25 thousandths of an inch per degree, per cam degree.
Yeah, that's just.
Oh, it was
my
like,
God.
I was young and I didn't know better, you know.
Who cares?
It's all right.
Yeah.
Makes for some interesting dyno tests.
Let me. The first time that I even knew who Billy was actually a conversation that I was having with Harold Brookshire, and you remember Harold, right, Billy?
Oh,
Very
yeah.
well.
So Harold was trying to describe to me the difference between different cam designers, between Harvey Crane himself, and he goes, and Billy over at Comp, and he goes, I'm the guy that I like to make sure all the horses are in the barn before I shut the door. He goes, Billy wants to make sure that he shuts the barn door before any of the horses escape. He goes, it's just a different way of doing it, neither right or wrong. Does that make sense to you, Billy, how Harold phrased that?
No, it's actually a tremendous description of what's going on. When Harold started to understand that peak piston velocity happened at 70 degrees after TDC, he became very conscious of front side area. So he was really, really, really working to try to, from 70 to 100 degrees after TDC, he was trying to maximize lift in that range. As we started to do more modeling and more work, and it really started back when, Harold was the cam designer for a few years at Comp Cams. And a couple of the profiles that he, or probably would have been, this probably would have been Mark Heffington's design. They're pretty similar. If you looked at what they did, every now and then we would mess up and flip a master on backwards, and it would run better.
Oh, okay. What? Okay. I'm supposed to be on mute. Sorry. What?
and it sort of freaked people out. So if you would think about this, like Bob Glidden, one of those seasons where he won every race, that engine had a flipped over master in it. And the season was over before we got the cam back and were able to measure it, figure out that it was flipped over. And we started changing the way we designed cams at that point. And it stayed for about 10 years that way. And then the springs got better, and we went back to cams that are a little more like what Harold would design. But Harold was very much he was kind of the John Daly of cam designers, the what they call it, grip it and rip it. So he would open the valve as fast as he could, and then he'd put longer closing ramps to try to get it to calm down. And the problem with that design is it works extremely well around peak torque, because around peak torque, the port is good enough that it can supply that air demand early in that stroke. But as you get to peak power and past peak power, now the port momentum, the momentum of the air, the air in the column has mass. So just because you have the peak signal at 70 degrees doesn't mean that peak velocity can't be at 100 degrees or 120 degrees or 140 degrees. In fact, as we've done more and more modeling today, we see that, in a pro stock motor, its peak velocity, it's still very, very close to peak velocity at near bottom dead center. So it changes the way you design a camshaft, that getting the horses in the barn, you're actually getting a lot more of them in the barn right before you close the door. So what you can do on the backside of the lobe is crucially important, especially in the engines that we build today. If you go back and look at what Ultradyne was super good at, and they probably had more than 50% of the market in your Saturday night dirt track, small carburetor, 350 type builds. And the reason is those motors really made best power. They ran best around peak torque, coming off the corners. Those cars were set up. The tracks were very tacky. They had plenty of tire, and the passing all was set up by who got out of the corner the best. And so if you look back at that time period when Ultradyne was at its peak, his designs that had those super fast openings, those are the ones that were really, really dominant in that type of racing. But if you look at the racing like Competition Eliminator, you would be hard pressed to find a single Ultradyne sticker on a Comp Eliminator car, and pretty much for the same reason, that philosophy of cam design works really well around peak torque, but it's very, very poor past peak power.
So are you guys looking, hang on, just a question. Sorry. Are you looking at, when you talk about monitoring how much of the horses you're letting in the barn with that intake valve event, are you looking at intake port pressures or combustion pressure or combinations of both or what? I mean, I've done a little bit of TFX use and have a TFX setup. Are you doing something similar there to kind of decide on your events, or how do you figure that out?
In most cases, you just look at the indicated power on the dyno. You make a change, see where you changed it, and then you can just look at the dyno and go, hey, I've got more lift at bottom dead center, and I closed earlier. That makes more power. Therefore, it's got to be the horse. It's kind of deductive reasoning. But we have set up the dyno with 3 pressure ports in the intake runner and a in-cylinder pressure. And then you can actually watch the waves. You can see what's going on. And then we go back and use things like we use a lot of the, I don't know, a lot maybe more than that's true, but a few times a year I'll get out Dynamation to try to really look at it, what's going in a motor, and I'll work Dynamation until I get the port to act like it really works on the dyno. So I put in cam A, I get the port and everything, the links to tune like it really tunes, and then I do cam B and make sure my model still works. Then I'll go look at the port velocities like you'll see in Dynamation. And occasionally we'll get systems that we can go into GT Power with a NASCAR team or with an OE, and we'll put the system in GT Power and look at that. That's one of the neatest things about. I talk to young FSAE students all the time that when you're a development engineer, you kind of are sitting on a 3-legged stool. One leg of your stool that often old people lean on too heavily is tribal knowledge, the experience you have. The other leg of your stool, the stool that I like to lean on probably more than you should, but I certainly love it the most, is testing. And your third leg of your stool is your simulation programs. And a poor engineer leans too much on one and doesn't spread the load out among all 3. A good engineer balances that better. A great engineer uses each leg of the stool to make the other leg of the stool better. So I want to use my testing to make my tribal knowledge better, our group understanding better. I want to use our testing to make our simulations better. Then I want to use our simulations to make our testing better and to make our tribal knowledge stronger.
Yeah, that's a great point. That's something I've tried to teach because I would consult for my old Formula SA team as well, and just in engineering in general, like that's definitely a great way to put it. If you're looking at tuning that way,
you will rarely see 90% of FSA teams will go and build a intake manifold in GT Power.
Yeah, I mean, it was like pulling teeth because this always made power. Yeah, you're right, leaning on one of those legs, not going back where you said where you'd go back and verify. You would tweak your model till it worked, then you'd run on cam to make sure your model is good because you've got your data. Now you go back and use that. You've got a model, you've got your data. So many guys never go back and run that through, whether that's, hey, this happened on the dyno.
Right.
This is what I saw on the track. Why do these match or not match?
Oh, absolutely.
Billy, this is Bill Fowler. Mark introduced himself by reminding you about a Pontiac with 2.1 rocker ratio, and he was trying to make 900 lift on 240 duration. Engine Masters engines have a tendency to have those huge rocker ratios and a lot of lift relative to duration. Could you unpack that a little bit for people? Because you look at those and think, well, that should work good in a street car. Maybe not. Can you kind of unpack why that works for them and what people might need to be thinking about when they're trying to build these ubiquitous street strip cars we hear about?
Right. Well, Engine Masters is probably my favorite idea. You know, I grew up sort of in the NASCAR world, and the professional NASCAR teams used to call drivers left side weight. You know, so anything you can get left side weight, you know, that's what we like about Engine Masters. But one thing is that I don't think people grasp is that Engine Masters at some point becomes a little bit more like comp eliminator than street engines. And also the scoring system, it does something that street cars generally don't. You know, John could probably talk to you about this more than I could, but a lot of high-powered street cars are very, very traction limited. So you might give up 40 foot-pounds that you can't hook up to gain another 20 horsepower up top that you know you can get to the track.
Yes, sir.
In Engine Masters, they score the same at 3,500 as they do 6,500. So you absolutely, positively, if you want to be a competitive participant in Engine Masters, you have to focus at the low end every bit as much, if not more so, than you focus on the top. In fact, if you don't have an engine that's leading at 5,500 RPM, you're not going to win. You know, if you look through all the tests, you know, if you look through historical data, the strongest engines were always super good low. And so because of that, what you'll wind up seeing is you're going to see a lot of short duration camshafts. Yep. You're going to see super tight lobe separations because these aren't, Engine Masters isn't a transient response test. You know, you load the engine on the dyno, you let it stabilize, and then you let it accelerate at a certain rate. It never occurs. I mean, if it does occur, it happens early on in a boat or in a bondable car. But in general, there's a lot of RPM changes in a car. There's a lot of throttle changes. So Engine Masters isn't really simulating a real world application. It's simulating its own self. And so that's why you're trying to see the Engine Master stuff with lobe separation, less exhaust duration. And if any of you guys have spent much time on the dyno, peak torque is where you have peak air demand, kind of like I mentioned before with the answer to Mark's question.
Peak volumetric efficiency, yeah.
Right, PVE. So if you want to increase power at peak torque, generally the valve is actually more of an obstacle at peak torque than is at peak power. Your timing points are hurting you by being too small at peak power, but your port capabilities are hurting you more at peak torque. So basically you want to get the valve out of the way as much as possible, and you want seat timing that's set to make the best torque possible in that 3,000 to 5,000 RPM range. And then you're trying to do everything you can with your cylinder head design and the rest of the engine to let it carry on past there to whatever their max is that year, whether it's 6 or 65 or 7 or 75. But you've got to do all your business early, just like in an NHRA super stock car. The mile per hour is there for the glory, but the guy's going to win the race is the guy who gets off the line the best.
Thank you. That's a great answer. Translating that a step over, we spend a lot of time on this podcast dealing with particularly LS turbo applications, and that seems to have become an entire planet of its own. You explain a little bit about this idea of turbo cam versus stock cam and what people should really be focusing on in order to optimize a combination around cam and valve train?
You know, the cam and the valve train is one part of the system, but it really is a system approach to everything. You know, you have to figure out what is the camshaft, what are you trying to do with the vehicle? You know, if you had one car that's got a 5500 converter, the guy brings it up to 5,000, releases it, it goes immediately up to 6,500, and he shifts at 8,500. You really don't care at all what that application does at 3,500. And you really don't care how hard it is to tune to go get groceries or pick up your kids. So, you know, the idea, I hear a lot of people say that there's nothing special about a turbo cam. And, you know, John, I'm going to steal your quote here, if you don't mind me doing it.
Do I need to get ready on the mute button? The
No,
mute button?
no.
Okay.
Hey, Billy. Hey, Billy. Can we hear the story behind the quote first?
John, do you want to open up with a story? Because this thing's too good. Because I know we were just having a rap session someplace talking about things.
Is
Yeah.
this the Jupiter story?
Yes, where you just blurted it out.
You know, I guess it was like 4 or 5 years ago. You know, I was just sitting here thinking, and you know, it never set well with me when everybody, you know, for the longest time, everybody was talking about boost is a restriction, boost is a restriction, boost is a restriction, and it just never set well with me because it's not, and there's just something about it that didn't sit right. And it just, you know, it can't be a restriction. It can't be. The motor's still flowing air. Horsepower is going up. If our horsepower goes up, it can't be a restriction. All boost is a difference in how much air the turbo's putting out and the volume, just the volume that the engine can consume. Now, the volume that the engine can consume is fixed because the displacement and RPM is fixed. So that's a constant. So the only variable is density. So I'm sitting watching a damn documentary on space one night, and they start talking about Jupiter, and they start talking about the density of the atmosphere. And then for some reason it just clicked, and I got to start thinking about the first book on turbocharging that I bought back in 2001 is Corky Bell's book. A lot of the calculations and stuff in that book were done in atmosphere. Well, you convert, the metric system and the British and people in Europe, they measure boost in bar, and bar is equal to atmosphere. Mm-hmm. Well, that's all boost is artificial atmospheres. Okay. Well, you start thinking about it. All you're doing is elevating the atmosphere of the engine above our natural atmosphere here on Earth. And I called Billy and I'm like, I just had an epiphany. Like, you know, if you look at boost as just a density factor of the air that the engine is consuming instead of looking at it as a restriction, it kind of changes the way you look at airflow through the motor in a dynamic, setting, because, you know, an engine is a dynamic thing. It's not static. It's not a tank. It's not just an air tank that you fill tires up with, right? Because it's constantly moving. So that's the Jupiter story. So, like, you know, 30 pounds of boost is like, it's like the motor being NA operating on a planet with the density of the atmosphere on Jupiter instead of the atmosphere on Earth. And you just have to think about, you know, what's going on in the intake, what's going on in the intake port, what's going on in the chamber with the air density 3 times that of the natural air density of our normal atmosphere.
Right. And I think, we were sitting there talking, and I gave this conference back in 2001, the PTC conference out in California. We started talking about, a lot of the old turbo books were written by guys when turbos weren't nearly as good as they are today. I'm sure they're like David Vizard has some books out there, and it's with the 2300 Pinto, but it had, 2.5 to 3.5 times more back pressure than boost. So when you talk about turbo cams versus NA cams, that there can be a lot of different boost to back pressure ratios. The first thing that we like to ask, John has the huge advantage of generally he's building the whole system. So he knows what RPM they're at. He knows what turbo they have. He knows about what back pressure they have. A good turbo system, like John said, a good turbo system is like drag racing on Jupiter. You've got a lot of pressure coming in. You got a lot of pressure coming out. They're about balance. So it's like an NA with this super good head with this super dense air. And I just love when he did it. So I've stolen that, that conversation. I've stolen that. A good turbo system is racing on Jupiter, I guess without the atmospheric drag. But, that's one of the things when people talk about turbo cams, people don't put enough emphasis on how much differences there are on back pressure between systems. If you have a great dyno system with, 4.5, 5 inches out from the turbine going out, and then you put in a car and you put a full exhaust on it, my goodness, it's not going to run anything like, one's not going to run like the other. So you have to deal with the back pressure. You have to deal with all that, the camshaft. And I don't think people appreciate how important it is. And if you're just doing some steady state turbo tests on a dyno with a pretty good turbo and a real good exhaust, you might actually teach yourself some lessons that are wrong in the process.
I had a customer, he's got a 5.3. I did him a cam. We put a 491 S400 on it from Jose. I did the heads, the intake, the camshaft, rods, pistons. I set this combination up, intake, the oil pan, turbocharger all the way out. He wanted full exhaust. I did everything on it. I knew it was going to have full 4-inch exhaust. I got everything situated. I told him I wasn't happy about the full 4-inch exhaust. I've got 6 foot of 4-inch exhaust pipe after the turbine.
Mm-hmm.
The best exhaust for a turbo car after the turbine wheel is no exhaust. And he did it, and he ran it for a little bit, and he's like, man, I get to this certain boost level, and I have to start adding 5 pounds of dome to get 1 pound of manifold. And I'm like, yeah, because you've got post-turbine back pressure. You've gotten to a point where you're choking the wheel. The exhaust that's post-turbine can't get rid of the exhaust fast enough after the turbine to clear out what's in front of it. So we've got this choke situation. I said, so you've basically gotten to the limit of what your 4-inch downpipe exhaust on the car can do. Mm-hmm. He's like, okay, I'm putting a 5-inch hood dump on it. So he puts a 5-inch hood dump. We've got 18 inches of 5. So we've gone from 7 foot of 4-inch to 18 inches to 5-inch. He goes out, makes a hit. The car, he leaves the tune up, the boost control settings exactly the same, changes nothing.
Mm-hmm.
He puts the car in the beams. The car makes 6 more pounds of boost in the staging lane, in the staging beams with the 5-inch downpipe than it did with the 4-inch full exhaust. And it kicks the tires first hit. He comes back, he pulls 15 pounds of dome off of it, still makes 3 more pounds than what he normally leaves with, kicks the tires again. He had to take 30 pounds of dome pressure off the wastegates to get the boost level back to the exact same boost level with the 5-inch downpipe that he had with the full 4-inch exhaust. Now, and down track, he's 40 pounds of dome pressure on the gates less to make the same boost that he had with the full 4-inch exhaust. Pressure ratio across a turbine works both ways, right?
Yeah, right.
So for every 1 PSI of post-turbine back pressure that you have if you've got a pressure ratio of 2.5 across your wheel, you'll create 2.5 of pre.
Mm-hmm.
So if you've got 10 pounds in the downpipe because your downpipe's restrictive, you just added an extra 25 pounds of pre-turbine pressure just because the downpipe's restrictive. You know, not because the wheel's restrictive, but just because the downpipe's restrictive. You can't get it out quick enough. And that's one thing, you know, like I said, the best exhaust for a turbo car after the turbine wheel is no exhaust. The quicker you can get it outside the body, the better.
Now, John, back when I had my Buick Grand National, that's not what they said in the forums. They said if you didn't have back pressure, it wouldn't spool.
I don't even want to start that shit. Don't even get started on that. You know, I don't even want to get started on that. You know, we were talking about Billy was talking about drive pressure versus boost pressure. You know, with the way that I set up my stuff, I start seeing power go away at about a 1.25 to 1.3 to 1. So if I've got, 20 pounds of boost, if I've got 30 to 35 pounds of drive, that drive starts any more drive than that, and it starts choking the motor up. So, that's when I have to start playing with what I play with to manage that ratio and try and control that drive pressure. But, in my opinion, the whole job of a camshaft and a turbo engine is to manage the relationship between the positive displacement pump, which is the engine, and the centrifugal air pump. Because all the turbo engine is a compound air pump. It's a PDS pump and a centrifugal pump. And the camshaft's job is to control RPM range and do all that, and then to control the pressure ratios between the two pumps.
Mm. Yeah, I think that gets back, we circle back to where we started chasing the squirrel. But sort of the question is there any difference between an NA cam and a turbo cam? And the answer is absolutely yes. And not only that, but there can be very big differences in a turbo cam for something with a small turbine versus a big turbine with a restriction behind it versus an even bigger turbine with no restriction. And
you can have three 76 millimeter turbos. You can have a 76 75 precision, a 76 S400 with a 96 132, and a 76 GT55. And we've got a 111 by 103 millimeter turbine, a 96 by 88, and then a 81 by 75. All three different turbine wheels, and all three of those turbochargers, in all reality, need to be cammed a different way. You can't put the same camshaft on all three of those turbos and expect the same result from all three.
Right. The bigger turbo with the better flowing is going to want to operate in a whole different range. So you wind up camming in a different range. And the density of the air, like you talked about, one of the things that people think is when they go to a turbocharged system, that when they increase the boost, that they're actually increasing the velocity through the port. And when you start doing the pressure waves and start doing the simulation, you really look at it closely, the actual air velocity can go down, and that's why the camshafts are generally shorter for the same RPM. That you actually got a little less air velocity. But the velocity that you have, it's kind of like drinking Diet Coke and then drinking a Frosty. The Frosty may be moving slower, but it's putting a whole lot more calories into you. So you kind of got to approach it a little differently than people want to. They want to oversimplify it. And I understand why. And if you're really just trying to go out there and make, 800 horsepower with the turbo LS, my goodness, there's about 800 ways to do that, and all of them are okay. But if you really want to do things at a high level, if you want to be a competitive car in a class, if you really want to go and do things right and not be super hard on your stuff and perform in the RPM band that you want to perform in, it takes a lot more than it does just to go out there and try to make an 800 horsepower glory pit.
I just want to see somebody take an NA cam that's ground on some EHI lobes or some LSK lobes and stick that in a turbo motor and see how long the seat.
LSK lobes have happened. They generally are those ones that are about good to quarter track.
I want to see how long the seats and the valves stay in the heads.
Is this what we discussed a minute ago, that it had kicked all 8 by the 330 or whatever it was?
Those are in the same. Yeah, those lobes are in the same families. The lobe that was on that cam for Duttweiler and the LSK lobe, they're in the same group of family of lobes.
Yeah, generally, if I have a K in a lobe family, that generally stands for kill. So someone somewhere couldn't kill their spring. And so anytime you see a K in a lobe family, just know that, that I was probably thinking bad thoughts.
So Billy, go ahead, John.
Yeah, if it's got a K in the lobe family, that's not meant to go in a street car.
So, Billy, this brings up a really, really interesting subject is when you go to the K lobe, how important does mass become, and where is mass a detraction, and this comes up to the group subject that we had earlier today when people were talking about titanium retainers versus tool steel, or a conical valve spring versus a beehive, or and I said, well, all components have mass. The spring has its own mass. The push rod has its own mass. Where does mass become critical, and where do you need to add mass to stabilize things?
Generally the adding mass, what we want to look at is a good friend of mine. He's working in Formula One now, but he came up with a term when he was at DEI called specific stiffness. And basically what he did is when he designed a bunch of rocker arms, different components, he would compare their moment of inertia to their stiffness. And so it's, where am I gaining stiffness to the system when I gain mass? One check that I want all professional racers to do is when they get a camshaft, get a rocker and system put together, the first thing I want them to do is take the spring they're going to use, make sure where's it coil bind, set it, check the lift with the flow bench spring, and then check the lift with the spring you're going to run. Say you're going to run at 60,000 combined. You know what the load is. Go and measure those two lifts, and you're going to see deflection. So, just to make it easy, if it's an inch 030 with the checking spring, and then it's an inch with the real spring, you've lost 30 thousandths of an inch. So now we know the system has a system stiffness like F = KX. So we're looking for K. So it's just pounds per inch, right? So if it's 1,000 pound spring, divide it by your 30 thousandths, 0.03, and now you know the system stiffness. A lot of people talk about adding mass to a lifter or adding mass to a push rod and trying to make them help you. It can happen because there's a frequency domain to it. But generally, you want to go with the lightest push rod you can so you can go with the lightest spring you can. But you don't want to give up system stiffness to get there. So that's the whole deal. If the rocker arm is super flimsy, there's no reason to put a super heavy push rod with it. So if you start measuring system stiffness, doing that deal, and if anybody needs me to do it, I can post it or whatever. But, that formula, it's just delta lift, change in lift, and the change in spring force. So if we assume that a flow bench spring is 0 pounds, which is probably about 10, and the real spring they're running is probably 500 to 1,000 pounds, it makes the math really, really easy. But I think I missed something I wanted to talk about there for a second. I'm trying to figure out where it was, but you were talking about the K lobes. Generally, when I do a K lobe, it means it has two things going for it, or against it, or with it, or whatever. One, it has very high acceleration rates. And we know that F = KX. So, F = MA, sorry, Hooke's law to, Newton's second. So for any given force you put in it, you have your mass and your acceleration. As the acceleration goes up and the mass of the valve stays the same, it requires more force to move that. And the other thing is, I talked about it, not only does it change higher acceleration, it has higher jerk rates. The jerk rates are how quickly you're applying those forces and taking them off. And they're proportional to the high order Fourier terms of it. So what you'll generally see with a K lobe is some of the smoothest lobes we have are K lobes. And they're absolutely baby smooth until they're not. And when they switch, like Mark, I'm sure that one of your camshafts for Engine Masters was probably based on the TK series. It was a lower lift TK lobe. But the deal is you were only turning that year, I think, 7,000 RPM, 7,200?
Or 6,500 or 7.
That was a 6,500 RPM year, and I think we were losing control of it at like 69.
Right. And the crazy thing is it's funny, I'll have customers take a TK lobe on a circle track, and they'll call me up and go, Billy, how much does it cost to get that combination put on the Spintron? And I'll tell them, dude, it's a waste of money. You go, what do you mean it's a waste of money? Like with that TK lobe, just go to your dyno, have your hand on the handle ready to pull back, let it run about 500 RPM past where you're going to run on the track. And if it makes any bad noises, yank it out and put a different cam in. If it doesn't make any bad noises, it's probably just fine. A TK goes from in control to out of control like you had turned off a light switch. And that's very common with all the most aggressive camshafts. They're generally very happy until they're very unhappy. Unfortunately, in the turbocharged world, like these turbo LSs that John was talking about, you've got the combined system, so the turbo may be getting really happy right when the engine's getting really unhappy, and the turbo in that compound system can drive the engine where the valve train is totally out of control, and then it starts spitting valves out, which is what happened to Duttweiler, and it's what happened it's happened to a number of people.
And it amplifies when you amplify the pressure in the system and you amplify the density of the air in the system. And you mentioned something a little earlier in the conversation I want to come back to, because you basically just validated something that I've been preaching for the last 7 years. It amplifies everything that happens in the system. So, when it goes bad, it goes really bad. The amplitude, when it goes out of control, it goes way out of control.
Yeah.
And, that's something that I feel you and I have collaborated on and worked on in the last 5 years. When I started doing this and we started working on turbo cams and I started doing my deal, there wasn't a lot of forced induction specific lobe designs that you had. We had slow stuff that worked, but
right.
Then, you've really started on, you've done your own testing there at Comp. You've dynoed and worked on a lot of turbo specific stuff. And you've developed a lot of lobe designs that have become forced induction, turbo specific stuff that the stability on is just crazy good compared to what you gave me to use 5 years ago. And you can see it in the dyno graphs because you can watch the thing go pull upstairs, and I can spot when the thing goes unstable.
Yeah.
And you can see where the valve train goes out of control. And, it's that point's moved up hundreds of RPM from where it was, 4 or 5 years ago,
yeah.
On the same duration lobes.
Yeah. I don't think we understood just how important good valve train dynamics were in turbo systems. The turbos were growing in leaps and bounds. At the same time, our cam design, there were some things going on behind the scenes in the professional race side that we really couldn't bring to the mass market till a few years ago. And what happened is we just had a real synergy. There was a lot going on on the professional side. There was a lot going on in the turbo side. And there was a lot of people who just had this amazing inertia they had a cam that they liked to run and they didn't want to change it no matter what. Hey, I won a race with this in 1997. I'm going to go to my grave and I'm going to run this profile. And the great thing about working with you, John, was that we were able to go in there and get into it and try some newer. Basically, it was the beginning of our low shock series that we've been pushing pretty hard lately, that you started to put in the turbo side, and just absolutely, it was amazing how quickly, we saw an improvement in performance.
Yeah, and we started off with stuff, and then we updated, and then I think we updated again, and it's been the stability of what we've got, and then not only did we do the hydraulic roller stuff, we did the same thing on the solid roller side too. Yep. We had the solid roller lobes that worked, and they did well, and then you started working the lobe development for the low shock, and then they worked even better. Our spring life got even better. Some of the new stuff that we've got, my guys are taking engines down. I've got the engine builders pulling stuff apart, and they're calling me when motors come down. They're like, "Dude, we lost 15 pounds. This engine had 150 hits on it this year, running X and X fast. These springs only lost 15 pounds from the beginning of the season to the end of the season." And,
between the spring developments that we see and the lobe developments we see, we're honestly seeing drag racers now where they change valve springs out of guilt. You know what I mean? It's just like, I used to get 20 passes. I'm looking at 120 now. I feel bad. I'm going to change the valve springs.
I got one car that's got 500 hits on set springs.
Yeah.
Is there a rule that you guys would like to suggest people follow for when you do need to look at valve springs? Because I've had a sort of a 2-year cycle on mine, but I don't have a great basis for it. And sorry about the dogs.
No, hey, I love the puppy. I think I got a turtle in my background, so hopefully it won't make too much of a mess.
More animal friendly.
No, it's a great question. One of the things I like to recommend people to do is when they're checking their lash, I really like people to check lash more than they change lash. So, if it hadn't moved more than 2 thousandths, don't go in there and loosen it and mess around with it. Just keep it and log it. So if you have a log book, and if you'll go in there and get one of those head-on spring checkers, they're not super precise, but they're very repeatable. So just go in there and have a certain springs that you go and you pull, and just log the load on it. And then when you go look at the valves, check the spring load again. Usually springs will take a few pounds set right off the get-go, and then they'll just flatten out and stay the same. And then at some point, they'll probably take another set. So if you see it taking that second set, you really have you really need to get it to change. But a lot of times it's just one of those things that, man, is it so much cheaper to take a spring off when it has 20% more life left than it is to take a spring off when it's 2% too much.
Makes perfect sense. Along those lines, Mark brought this up a minute ago. We've seen this interesting evolution over time, triple springs, doubles, and then kind of following what the OEs have done with beehive springs and then conical springs. And again, so many of our listeners are in LS world, and dare I even speak these words, modular world or coyote world, never mind the 7.3 coming up. What's the thinking?
Shut your whore mouth.
Yeah, I know. What is the current thinking these days about, springs in these kind of applications that use those kind of, factory springs, and you're doing those first stages of upgrade?
Well, Mark really brought it up when he talked about every component in the engine in the valve train has mass. So everyone's seen this change from the big heavy triple springs Most people are away from that and onto a double spring, at least on the exhaust side. Now, some of the fuel cars are still on triple spring. Some of the pro stock guys still run them on the intake. And it's a hard dance trying to get back from a 1,500-pound open pro stock triple back to a 1,300-pound open pro stock double. And that's something that, if you ever win the lottery and are mad at your money, come over to my place and we can have a ton of fun figuring out which one's best. But for most people, like we redesigned just recently for the the Power Tour guys, we took our very popular triple spring, the 947-16. It's a common late 90s triple spring used in a lot of bracket cars. And we redesigned that basic spring with very similar specs, but in a double spring. When we did it in the double spring, because of the less mass, that new double spring, we called it a 26,547. So keep the last two numbers to let people know what's going on. That double spring will last 4 times as long as that triple spring. So it's pretty amazing if you can take the mass out and use some of the latest wires, what you can do with the spring design today compared to what you could do in the 90s and early 2000s. When you get to the beehives are an interesting step in technology. The ovate wire is problematic trying to hold the orientation of it when you coil it. Man, they're nice. When we went from the big, heavy, ugly doubles to the beehives, man, we thought we had found the cure for cancer. It was the best thing that ever happened. But as we started pushing beehives more and more, we even made a pro stock beehive. And boy, was that ugly. Now we've come along to the conical technology. The conical springs use a round wire, and the round wire can be made in the very highest grades available today. And so that really helps. The other thing a conical does is that the bottom 3 coils of a beehive are generally the same pitch and they're the same weight and they have the same frequency. On a conical, every coil has a different frequency, a different rate, a different natural frequency it wants to vibrate at. Also, the conical, as it gets close to coil bind, it nests in itself. And so there's some very, very neat damping that goes on between each coil as it goes toward coil bind. A lot of times on the conicals, we'll see customers run those 40, 50, 60 thousandths from bind and use that dampening for a really neat, it really works pretty neat. So I'm as excited about the conicals. And one thing we're never able to do in the conicals is the beehives is make a race spring. On the conicals, we have a part number 7245. And our friends over at EFI University, Ben Schrader's been working with that, and he's been going, 825 lift at 10,000 RPM with some of the new low shock lobes with those. And it's been a really, really neat deal that we've done. So we've had a ball trying to learn how to use the conicals. And that's a technology I think.
How many guys are running them like 10 from bind or running them 2 bind?
Well, that's a real good question, because what does it mean to run something? Say if I say 50 thousandths to bind, is that 50 thousandths to bind from the spring you're running, or is that 50 thousandths to bind from the checking spring?
Well, when I talk about it, it's the spring that I've got in the spring tester.
Okay, so here's the deal. A lot of the push rod motors will have 30 thousandths, 40 thousandths deflection. So if you actually try to run those if you have something that has 40 thousandths to deflection and you run it 30 to bind, you're actually driving the retainer down. You're actually running the whole system in compression over at max lift.
Right.
So that seems not to be the best, as we've been looking at, that's probably not the best way to do it. What I like to do is to be about 40 thousandths from bind from the checking spring, so that you have a little bit of fudge factor there. So you're not driving it. My wife is she was a Montessori teacher for years. And I don't know if you guys are familiar with Montessori school, but they kind of have an open format where the kids can all move around. They do different works. They bring them back to their area. And I watched her one day, and some of the boys, she was teaching like second or third grade. And you can see some of the boys that get really fidgety. And the cool part is I'd see her walk over and sort of just put her hand gently on the little boy's shoulder to kind of get him to kind of calm down and quit fidgeting. And if you watch the dynamics of a valve spring, they're kind of like a third grade boy. Yeah, they're wiggling and jiggling every which way that you could imagine. And so watching, use that coil bind to kind of like my wife would put her hand on the shoulder, using that distance to coil bind just to calm down those surge and oscillations. Now, notice when I said she put her hand on her shoulder, she didn't come back and slap him upside the back of the head. Now, with some kids, that might work, and with some springs, that might work. But when you start driving one to coil bind, you're no longer putting your hand on its shoulder and asking it to be still. You're slapping upside the head and telling it to be still.
Yeah, so I think you misunderstand how I'm measuring it. What I like to do is put the actual spring in the engine and measure how much lift I actually get out of the engine. And then I'll set it up to run, depending upon what I'm doing, anywhere from 30 to 50 from that measured point. So I'm setting up 30 to 50 from the actual bind of that particular spring. But I know that there are people that run them down like close to 10.
Yeah, and like I said, your deal is my wife's deal. You're putting your hand on its shoulder and stopping it from fidgeting at 40 thousandths. If you run it to 10, you're slapping it.
Got it.
And some third graders need slapping.
Beely, I don't think you got slapped enough. Go ahead.
I probably didn't. No, I know I didn't.
Oh, my mic was turned on. Shit.
So, Billy, you've kind of explained as to why a lot of the excitement is around the conicals, and that was a nice explanation. And so as we see conicals become a bigger and bigger deal, we'll all know why. It used to be the big upgrade was titanium retainers. Now, I've run a bunch of titanium retainers on a 900 lift, pump gas, drag week, big block deal, and we ran into issues with galling and other stuff, so we switched over to the tool steel. That was just one application, one thing, but where are you guys now on this whole stock retainer, upgraded retainer, aluminum, TI, tool steel? How should we think about that?
Well, Bill, that's a great question. And, it's funny how well the conversation I just had with Mark fits into your question, because Mark and I were talking about very, very subtle differences in distance to bind, right? We were talking about 30 or 40 or 10 or 50 or 60. And we were saying it mattered whether you set it up at 30 or 50 or 60. What happens on a titanium retainer when the retainer wears 40 thousandths through the life of the retainer? What's your distance to bind if you have to date stamp it? On pass 1, I'm 40 to bind. On pass 30, I'm 50 to bind. On pass 60, I'm 100 to bind. You can't. That's the biggest issue with the tie retainer, is it's constantly wearing. It's constantly putting titanium in your engine. When you design one, if you know it fails at 40 thousandths cross section, you design it 100 and let it wear, 60. You're really in a whole bunch of issues. Now, on triple springs, it seems like having that extra titanium. If you've ever ridden a titanium bicycle, compared to aluminum bicycle, titanium is almost as strong as mild steel per volume, but it's not nearly as stiff. That's why I never see a titanium rocker. It's not very stiff. So on a big triple spring with as far out as that outer coil is on a 1/650 triple spring, probably having a titanium retainer on that's pretty good, because it's big, fat, and dumb. And what you're giving up with this kind of sloppy retainer and losing distance to bind, you're making up with by having something that's sort of compliant. When you get to the new, more modern springs, the double springs, the conical springs, things like that, the titanium, its benefit of lack of stiffness doesn't help you. And its drawbacks of it costs a lot, it's going to fail, it wears out, and it changes installed height. Its drawbacks hurt you more than your benefits help. So I would just say that you were going into the tool steel retainer, you were just an early adopter to a technology everybody was going to. If you really look at a modern tool steel, you know, it's approximately, if you look at the material strength, it's approximately 300 KSI. If you look at titanium, it's a little over 150 KSI. So basically, you've got a material, the tool steels are twice as strong as titanium, but they're twice as heavy. So if you spend enough time putting the mass where it needs to be, you should be able to get to a very, very similar mass with tool steel as titanium. But you won't have the wear on the spring, on the retainer like you see on the titanium.
Is there a certain spring pressure or surface area on the retainer to where the spring actually contacts it that has a wear factor, I guess? You know, obviously a 1,000-pound spring is going to, you know, wear the titanium retainer faster than a 300-pound spring.
There's a little bit of that, but honestly, what happens is the springs become, as the springs become smaller, as they become lighter load, they become smaller wire and smaller surface. So you always get the wear. You know, the NASCAR guys were running springs that were only about 130 pounds on the seat, and they were, say, 500 and some odd pounds over the nose, little 1-250 guys. And at the end of the race, whenever you took an oil sample, you could measure that they'd worn 20,000s. And two, whenever you did an oil sample, you saw when Lake Speed was working over at Gibbs, you'd see this big spike of titanium in his oil. So it was always wearing. It's just how quickly it wears.
So Billy, when are we going to see an ultra thin tool steel retainer with a bonded carbon stiffener?
People get really mad about $150 or $300 set of retainers. You know, when you start throwing out a $3,000 set of retainers, somebody's going to get mad at me. So I'll let somebody at Del West do that, and I'm just going to keep making the tool steel ones. Those, you know.
Well, see, that's another great thing about the Conical, because with the Conical, as the shape of that spring gets smaller as it comes to the top, you know, the retainer diameter is significantly decreased, which that decreases the required mass in the retainer, and you get a tool steel retainer that's basically at titanium weight because the diameter is not that large. So the Conicals are really interesting. That 7245, I'm really looking forward to getting that on a couple of cars and doing some testing and seeing how that works out on some of the turbo stuff.
You know, it's funny because I designed that spring was probably one of the best and worst things I've ever done at the same time. You know, I was just working on what can I do with the conical spring, not letting the outer and inner rub on each other. You know, having the way we did that dual conical where it's a non-interference dual conical. And I didn't really pay attention to the application. And when I got done with it, I had a spring that I really didn't have cam profiles for, and I really didn't have an application for. And, you know, like big block guys run more lift than it'll handle. Small block guys didn't have anything that would fit anything over 1/600 on the base zone. And so there was like, I actually created a great spring that had no home. And just out of blind luck, people started to work on these new cylinder heads for the LS that would handle the big bottom. And then we developed the new profiles, and all of a sudden we wound up with a package that's really pretty awesome. And it was totally unintentional. So if anybody ever gives you the choice between being really good or really lucky.
Yep.
I'll take luck.
Lucky with a touch of good is a really good combination.
Yes, yep. Exactly. If you can make the two meet at the same time, it's luck is when opportunity meets preparation. So you can make it happen.
Yeah.
So Billy, talking about your dual conical spring where you have different diameters and different cross sections, and that of course helps with valve train dynamics dampening. How about your multi-cross section, multi-piece adjustable push rod? Let's talk about that.
Oh man,
that thing is cool as hell.
You don't know how much I love this piece. It was one of the ones, because basically this all started because I wanted to race in a $500 class road race deal. And hydraulic lifters are one of those things that are a little. Hydraulic lifters never do the same thing twice. If the oil temperature changes or the oil viscosity changes or the oil gets aerated, it changes the duration of the camshaft. And so going road racing with the hydraulic, I'm like, I'm going to put this thing in a corner. I'm going to get bubbles in my oil and I'm going to crash the valves. And I can't be the head cam designer at Comp Cams and blow up valve springs on my $500 race car. So it's like, well, I love the rocker arm. How am I going to set the lash? So I was thinking, okay, I'm going to saw the stands in half and I'm going to shim them. I'm going to do all this stuff. And I got halfway through it and I'm like, man, it'd be easier doing the push rod. And so we started doing this setup to do the push rod. And about halfway through it, we decided, okay, let's put an FEA and look how strong it is and how much it weighs. And, it really fell in between the 7/16 and 5/16 push rod. And it should have performed like a 3/16. And we looked at the stiffness, just loaded it in a press, measured the deflection, weighed it, like, okay, this thing's going to act like a 3/8 push rod. And so we went to the Spintron and did the first test, and it's like, hey guys, this thing's looking way better than it should. And you can imagine how much that surprised us. So what we found out was, it was a long time getting back to it, but by having that big bottom section, that top smaller section, both sections have their own resonant frequency. So instead of going into resonance like a standard single piece 3/8, it has a higher resonance frequency over the top and a higher resonance frequency at the bottom. And it got me thinking back about the old Mauser gun barrels that the Germans made. If you go back to World War I and World War II, they had a stepped gun barrel. And I was always like, why would the Germans, they're smarter. I mean, you can't tell me the Germans weren't smart enough to move over the tailstock and turn a tapered barrel on a lathe. But it seemed like it was that. And I think what they came up with is by running the steps through the system instead of having one taper where it all wanted to go in resonance, by going into the steps, they did the same thing we did with the push rod by making one push rod into two push rods, and both push rods had a higher frequency.
Well, that's pretty cool.
I know those things. I know those things make life easy when you've got a set of short travel lifters that only have a 10,000 window to hit.
Well, each section is a lot shorter too, so you're increasing the frequency just by making it shorter.
Right. You're doing a lot of good things. If you're over in Dubai and you're setting up a short travel lifter, like John said, having those XDAs saves your bacon, because you have the shim kit, you can set them up exactly where you want. And a lot of the people with the hydraulics, if you start setting them closer to the bottom instead of the top, if you have good dynamics, that works extremely well.
And then what's your turtle's name? Go ahead, John. Sorry.
It's got about 3 different names. Yoda is the one it usually goes to. But if you'll feed it, it'll let you call it whatever you want to.
Oh, I have some of those in my house.
And one thing we found out about the LS that never dawned on me for multiple years when I was doing this is the stock rocker rails in an LS is I really didn't realize how garbage they are as far as tolerance.
Mm-hmm.
instead of short travel lifters, it's got a 10 thousandths window. I had a customer set them up, and he comes back at me and he's like, "There's no way I can do this." He's like, "I've got a 28 thousandths variance from shortest to longest in my push rods, and you want me to hit a 10 thousandths window?"
Yep.
And he had one of the granite plates with a dial indicator, and he pulled the rocker rails off and he starts measuring, and the rocker rails themselves were 14 thousandths difference on thickness from one to another. And one rail had 10 thousandths worth of taper end to end, and another rail had 12 thousandths worth of taper end to end. And so, yeah, that anytime anybody tells me they want to put a short travel lifter in their engine, Comp short travels or Johnson short travels, they automatically take the stock rocker rails and throw them in the trash can. And I tell them that to save pulling their own hair out and buy $100 set of billet machined rocker rails, so it eliminates that variable, that tolerant stacking that a stock cast rail can create.
I've actually
tighten that up a whole lot.
I've actually had the rails where we put them on and the rockers are crooked, like they're off by 10 degrees or 15 degrees, where the whole tip doesn't even hit the top of the valve, or so
that too.
Yeah, they're horrible.
John, where's a good place to get those billet rails at?
I've got them. PRW makes them, and you can get them through Summit, you can get them through JEGS, you can get them through EPW. I keep them. They make them for LS1s and LS3s, so you can get them for basically any engine configuration that's out there for the LS. They're $99 a pair. Or you could do like good old industrious Brad Schneider's did and sand them straight if you have to.
Necessity is the mother of invention.
Well, when you own 10 soldiers and you've got a shop like that at your disposal, it can, you can pull stuff like that off.
But maybe the rest of us can't. Billy, you made a comment earlier about as soon as you know it's a K lobe, it's meant to be on kill. Is there a secret decoder ring for understanding which lobe series kind of relate to what? So if you're running RX, this, or a Rev drag race that, is there a way to kind of keep a sense of where you are in these lobe families? I've experienced this myself as we've tried to continue to sneak up on what we can get away with in a drag week application. And it's always like, well, we'd like more of this and we'd like more of that, but I don't want to, knock the valves out of it with a K. So absent having the conversations with you guys constantly, is there a way for people to look in the catalog and begin to suss that out, or do we just need to get on the phone with you guys every time?
A lot of times our sales guys and our customers that buy a lot of camshafts, they're both really good at figuring out what's going on. And we try to let people know a lot about what's going on. One year I had something that looked like a Thai restaurant. Mark, you probably remember this at PRI. I had chili peppers on each of the cam lobes in our lobe catalog. This is a 1 pepper, this is a 2 pepper, this is a 5 pepper, And so, you could move from a 3 pepper to a 4 pepper and not have to go all the way to a 5, or move back from a 5 to a 4. But it's gotten kind of hard to do that at this point because we have so many different profiles and so much new is coming out. But for something like Drag Week, we have a new series called the MMO series, and that's, instead of a low shock, that's kind of a mid shock profile. And that MMO series has just been so good in applications like bracket racers and especially the Drag Week stuff. That's, it's one of those lobes that you can run it until you get just at 9,000 RPM. It will run until you just get guilty with valve springs. And for the guys who are running Comp Eliminator, they're turning it well over 10,000 with no trouble. Of course, that's a much lighter valve than the guy with the bracket race big block, right? Because the bracket race big block's 140 gram valve going 9,200. The guy at Comp Eliminator is going 10.6. My goodness, I think his valve would float on water. Not literally, but it's below the NASCAR limit of what they can run. You know?
Okay, John, I'm resending you that CAM questionnaire. So let's get this right this time. I mean, not that you got it wrong, because we didn't do one last time, but I want to do one this time. Let's do it right.
Do it. And, you know, I mean, you know, your question is kind of a loaded question, because even me now, outside of turbo engines, when I get put in that situation, Bill, I pick up the phone and I'll call Chris Mays.
Yeah.
So, you know, I started working with Chris 21 years ago now, because he was my rep. He was the rep that I talked to, you know, with my first job in this industry. And he's continued to be the person that I've talked to, you know, the whole time I've been doing this. And, you know, he's the person I still have to talk to him about trying to figure out which one's the right one. Because if I go a week without calling and talking to him or talking to Billy's created 4 or 5 new load families. And what I used the last time in a situation's no longer what he want me to use. And there's something different. And no, this is what you need to use this time.
Okay. Continuous improvement.
You kind of just touched on what is so impressive about Comp and Billy, is because with all of the facilities that they have and all of the racers that they have out there, they also get an incredible amount of feedback. And what I see Billy doing is constant development, and all of these new lobe families come out because they're going to address this issue or this class of racing, or they're going to address that issue or that class of racing. And it changes so fast that you really need to have someone that you can talk to, because they're changing, let's say every 6 months, where maybe some of the companies that don't have the resources, they're only changing every few years. So that's the exciting thing with Comp.
Yeah, I mean, if you look at it, the last load catalog Comp put out was 16. The last printed one.
Mm-hmm.
You know, and there was like the end of 18 into the start of 19. Chris sent me an email with a consolidated. He consolidated all the load families together that Billy had been making, all the updates, all the latest and greatest, everything together, all of his Excel files of all the loads. I get this email, and there are 39 Excel files attached to this email.
Mm-hmm.
And so it's fun trying to keep up with him when he starts making and he starts getting into this new stuff, because like in the last 4 or 5 years alone, just working with me and what I'm doing on the turbo stuff, I can say for me alone, just on what I have put out to my customers, I would say the load count that Billy Godbold has made for me is well above into the 4 digits. Well above it, into it.
Holy smokes.
Yeah, just the solid roller list is over 200.
Yep. LXT, the TCXs.
Yep.
Because the LXT, you made me, there's 4 or 5 different LXT families.
Yep.
I mean, that LXT TCX series that you did, I know that page is 250 loads alone.
Yep.
So
we went to and looked, and it was, it's just amazing how much, but it's so much fun when you have people that are giving you the feedback. When you can test stuff, when you can get people to run it down the track, when you're seeing what things are doing. I mean, this isn't work, that we talked before we got on the line. We were talking about doing some like carb cam development and how frustrating and maddening it can be. Now, there's a lot of joy when you get it right, and it's a fun challenge, but it can just be brutal. But when you start dealing with racers, they're so excited to try something new that it's a lot more fun,
Well, racers are always looking for that little edge, and it's the enticing part. It's the chase per se. That's the thrill, I guess.
Right. And I don't mind, you know, the street cam and bringing out the best technology we can for different street cams. That's fun. That's rewarding. Doing stuff for carb. That's fun. That's rewarding. But when it comes to somebody who, if you can give them a little better cam, they can put their front bumper in front of the guy they're racing against. Man, that's just like crack cocaine. That's so much fun.
Thank you, because I really need something.
Like crack cocaine.
Ahead of Kurt Johnson.
So you want to. So here's the thing: is any project you work on, there should be some sort of a challenge in it, and it doesn't always have to be the most horsepower or the most RPM or the fastest. I did an engine for my wife's Tahoe that John helped me with. It's just a Chevy Tahoe, and it had started burning a lot of oil, high miles, and I told John what I was doing. I ordered a cam and valve train package from him because it's really nice to be able to pick up the phone and call John and say, "Hey, I'm doing this. Can you send me all the parts that I need?" And hang up the phone, and a week later, all the stuff shows up. Right? Probably not even that long because he ships really fast. Well, I put this 5.7 together. It's a iron block 5.3 that was bored to 5.7. So now I've got an iron LS1 in our Tahoe. Mm-hmm. It made 305 horsepower at the rear tires through factory catalytic converters, factory manifolds, factory everything. It looks 100% stock. And people ask me, how much power did the Tahoe make? And I'm like, 305. And they're like, well, couldn't you do any better than that? Well, of course I could. But the cool part about it is my wife drives it every single day. She's driven this thing for 200,000 miles, and she didn't notice that I changed the engine. And not only that, it picked up a half a mile a gallon.
He swapped the motors in the truck while she was gone one weekend. He didn't tell her he swapped motors. She got back in it, was driving it. Now,
like 2 weeks later, I asked her. Yeah.
Didn't tell her that he swapped motors, and this thing makes almost 100 horsepower at the tires, more than the old wore-out 5.3 made. And he let her drive it for 2 weeks before he told her he swapped motors in the truck. And she could not even realize, she couldn't even tell that the motors had been changed in the truck.
Yeah, I was really proud of that.
Yeah. Yeah, every project, if trying to do something with excellence, there's a reward to facing a problem and trying to address it with excellence. And that's what comes in when we're doing the street package, when we're doing the card package, when we're doing a ship engine or a go-kart engine or something for a weed eater. You still want to do whatever you do. You want to do it the best you possibly can do. It's just the thrill of competition is something that drives me in a way that the other side, there's a reward there and there's feedback there because everybody's so involved. I promise you the guy that's testing packages at the EPA lab is not nearly excited. He doesn't care. He's going to test this one. He's going to come in tomorrow. He's going to test the next one, where the customer that's doing the professional racing or doing the serious racing, the energy you get back from the customer is really cool.
Billy, we had a question. One of the listeners on here, Frank Reyes, he asked, please ask for dual pattern cams and single pattern cams. Looking for more info on that. I mean, this has been something that's been around since I remember reading about, Isky 3/4 race cams in the 1960s. And I've never had a cam in my life that was a single pattern cam, and anything starting, you're going to get a sense of this real quick with the 289s all the way up to the Stroker 460s. So I'm curious, how does this idea of dual pattern versus single pattern play out today?
I think what happens, if you went to an old Van Norman grinder, it was a lot easier just to put one master on it and grind the intake and exhaust and everything to the same profile on all 16 lobes. And you brought up a small block Ford. A small block Ford has generally only about 55 to 65% of the flow on the exhaust that has on the intake. So generally with a head like that, you're really going to pick up some power if you cheat the duration up on the exhaust. So engines like that brought about the dual pattern camshafts. And what people started to see was that the exhaust opening point, you start looking at, there's 4 valve events, exhaust opening, intake opening, exhaust closing, intake closing. And so if you want to move just one of those points, you can't do it with the same master on both sides. If I want to move the exhaust opening 4 degrees and leave the other 3 points the same, I need a 4 degree bigger exhaust, and I need a 1 degree wider lobe separation. Then I need to advance it 1 more degree. Then I put my intake at the same spot it was before. I have the same intake opening, same exhaust closing, same intake closing, but I've moved my exhaust opening. And since then, now, like what John was talking about on his camshafts we're making for him, he was talking about intake profiles and exhaust profiles. Not only are we changing the timing points intake to exhaust, we're actually putting a cam profile that's optimized for what the exhaust is trying to do. If you look at the intake valve, when it opens, not a lot's going on. Unless you have some weird supercharged application with no cylinder, no exhaust pressure, and 50 pounds of boost, when you open the intake, there's a ramming effect going on. There's an exhaust pulse that's come back that's trying to pull on the exhaust a little bit, but there's still residual gases, so there's not a big pressure differential. But when you open the exhaust, there's a tremendous pressure differential at exhaust opening. So there's a tremendous amount of mass flow right when you open the exhaust that you don't have right when you open the intake. So there's really no reason, based on what's going on in the engine, that those 2 profiles would be the same. They really shouldn't be the same profile family, and they really shouldn't be the same duration. And if for some reason they are, you were probably just lazy. If you think they were, you were probably just being lazy.
Well, I think that's as good an answer as you can expect, Frank. So get something that really fits your engine. I'm going to speak from my personal experience here by working with the guys at Comp and actually getting something that actually suits. It's never going to be something that's in the catalog. They've got, I don't know, how many lobes do you have now? I have no idea.
It's over 50,000 different profiles, not counting the different master sizes and journal sizes and everything like that.
Yeah, so get something that really suits your engine. You're going to spend literally a few more dollars and get so much better performance you can't even stand it. We had a question from a very different direction. You were talking about oil analysis. Mm-hmm. Is there a way that you look at oil analysis as a way to tell someone what's going on with the valve train? I mean, like you mentioned titanium. Are there things that are a clue for people to use? We've had Lake Speed on here when he was still with Driven, but are there things that you look at to say, oh, this is telling you what's about to happen with your engine and it might not be good?
Lake's one of my dear friends. In a lot of ways, Lake's almost like a brother to me. So I've looked at a lot of oil analysis with him. When we're looking at flat tappet cams, if I'm being really, really on my A game, I can tell when the phosphate stops wearing off and when it's through break-in. But I can't tell you where the iron you saw in it is from the cylinder bore or the camshaft. So I am not the expert oil reader. Generally, if I see something in the oil, like if you send your oil out and get a report back and I see something, it's a car wreck. It's like, hey, look, your guide, it's not in your engine anymore. It's in your oil pan. Or hey, you have titanium retainers. You should put red tool steel. If I see something in an oil analysis, it's generally something really, really bad, like a train wreck.
Billy, one of our listeners, Scott Liggett, says, I want to tell Billy hi, and with the exception of 3 times, he's used comp cams exclusively since 94. One engine has had 5 comps in it over the last 25 years.
Looking at that oil, Scott. Sorry, Billy, go ahead.
I mean, I can't tell you how much I appreciate our customers. We have the best, and we have the best customers, and so many of them become great friends over the years. And we appreciate people more than they will ever know. getting to do this for a living, not having to grow up and get a real job, and then the relationships that we've got along the way, it's a bigger deal than you could ever imagine.
Danny Bappert asks, with all the technology, does a solid roller and a turbo LS still make more power than a hydraulic? And I answered him. I said, yes, no, maybe.
Well, it's that the only issue you have with a hydraulic is, the limits that you used to think you have. John can tell you they're not as limited as you would have thought. But that deal that I talked to you about the hydraulic not sure what it's going to do and not going to do it the same thing every time, there's a reason why NASCAR engines and pro stock engines don't run a hydraulic roller. They'd be legal, but they wouldn't run them because they just don't want an oil temperature change to change the cam duration 2 or 4 degrees. They don't want an oil aeration thing to change the duration. A hydraulic, because the hydraulic mechanism is always going to have a little bit of uncertainty. But on the other hand, if you look at what John's done with that team out of Australia, my goodness, what you can accomplish with a hydraulic. And you would be hard pressed. Have you ever seen some of these boats with all the marine headers going off on it? You can be sure if I had a boat with 2 engines in the back, which I don't have enough money for the engines or the boat, that the engines would have hydraulic rollers in them, because the hydraulic rollers can be so good that I wouldn't want to go through the hassle of, having something where I had to remove the engines to check the lash.
So I'd like to address something along those lines, because he asked which one makes more power. And
solid will make more power.
Yeah, the thing is that a lot of times people will focus on a peak number on a dyno, and that's all they focus on, and they lose track of area under the curve. They lose track of the entire RPM range that they're using the engine in. And more than anything, that's what I learned from Engine Masters is it doesn't matter if it makes 700 horsepower peak if it's a complete turd below that. You've got, unless you have a snowmobile clutch in it where it runs at peak power at all times, you have to look at area under the curve. You have to look at average power and average torque and the RPM range that you're using it. So the question, does it make more power? It should be modified to, does it make more power in the RPM range that I'm using it in for the purpose that I'm using it for?
A good addendum. And the thing of it is it's like with GTO. The GTO may peak power at 8,400 RPM. Mm-hmm. How many people out there in a drag race application right now have really got the cojones to build an application that's going to turn more than that? How many people want to put something together that's a 9,500 RPM application? There's not a lot of hobbyists out there, at least not with the guys that I deal with, that are going out to build something that'll turn 9,000 RPMs to the traps, because they don't want to do the maintenance on an application that would be required to support something like that. They wouldn't want to change valve springs on that. They wouldn't want to change bearings on something like that. At 8,500 RPM, I don't think there's a reason to be solid roller.
Yeah, we did some testing on some packages, solid roller versus hydraulic roller. And we designed them so that they had almost exactly the same valve timing and almost the same area and everything like that. And I think the only advantage, and it's a very small one, is that when we went to the solid roller, that you get a little bit better precision in your valve events. And I think people don't understand that everybody runs variable valve timing. Like if I asked at one seminar one time, how many of you guys run variable valve timing? And man, the 2 Honda guys just about jumped out of the seat in the front row. They were so happy. And I'm like, well, who all's run a 4-stroke engine? And, everybody raised their hand, right? I'm like, well, guys, every one of you has run variable valve timing. The problem is it was variable the wrong way. At low RPM, your push rod, rocker arm, lifter, camshaft weren't deflecting very much, and your camshaft was too big. As you went up in RPM, everything started deflecting, and so the higher you went in RPM, your cam kept shrinking and shrinking like a sweater in the dryer. And a hydraulic versus a solid, when we looked at it, we could see that the hydraulic, gave up about, because the solid didn't shrink as much, that the average power was a little bit better with the solid. But I'm not we're talking a 600 horsepower motor here, and we're not talking about 10 or 20 horsepower. We're talking about 5, 10,
Now let's go put 35, 40, 50 pounds of boost on that and see what that 5 or 10 naturally aspirated turns into, at that point. And it's not necessary.
It's probably not going to be a tenth of a second down the track.
Exactly.
I put a huge amount of effort into my 2-barrel program for many years running dirt cars, and we'd fight for a horsepower or 2 horsepower.
Right. Yeah.
Billy, on your latest stuff, what about, the latest stuff you're working with is like some of the coatings on the cams and the valve springs. You've got your black series from Elgin. What, the processes, the polishing, what are your thoughts on the REM finish stuff? Where are you at with that?
Well, we've been really big on surface engineering on camshafts, and we started that in about 2016 to 2018 was when we really got big into it. We actually spent about 5 or 6 years doing a lot of surface engineering with the profilometer. There's a lot of stuff out there that's not great. Like if I had a set of rear end gears for my car, I wouldn't have any trouble going with a rim finish. But I wouldn't want a rim finish on a camshaft. And the reason I wouldn't want a rim finish on a camshaft is on a camshaft, you've generally got a high carbon content steel. And rim is actually a chemical annealing process before you go through a vibratory finish. And the chemical annealing attacks the iron, but it doesn't attack the carbides in the surface. So you wind up with a lot of exposed carbides. So the NASCAR teams played with them for years because they knew that they put a rim gear in the back of their car that their oil temperatures drop. So they tried rim camshafts, and it cut all the DLC coating off the camshafts, off the lifters. So rim is really good in some applications. It's not great on a camshaft. As far as on a retainer, there's not a whole lot of good that you can do. I mean, we vibratory polish our tool steel retainers. There's basically 3 ways to polish. Well, okay, 4 ways. You can either polish something for 100 years, and get it really good finish. So that's way 1. If you don't have 100 years, you've got to speed up the process. And to speed up the process, you have to use energy. So what type of energy do we have? Well, we have electrical energy. Well, that's what electropolishing is. They use the electricity to speed up the process. The problem with that is it changes the structure on the surface. Okay, if I don't want to use electricity, I can use chemical energy. Okay, if I use chemical energy, what am I using? Well, I'm probably using acid. I'm probably annealing. And so, like I said, with annealing you can leave exposed carbides. So what's my third type of energy? Well, kinetic energy. And so what I like to see in all valve train processes, if you're going to go to a really high-end finish, I want to see a kinetic energy process used. And our MSE finish is a kinetic energy system. Does that make sense, Mark?
Absolutely.
Yeah, that makes sense. Yeah.
I had to get back over to the mute button. Sorry.
No, it's no problem. I just didn't want to. I wanted to make sure I handled that halfway decent.
Yeah. Well, some of this stuff I'm asking you, Billy, is so that you can talk to our listeners about some of the new products and the new technology that you're offering.
Yeah, the MSE stuff. I mean, like, to give you an idea how good the MSE is, on on a roller camshaft, we've gone through a lot of stuff that's going on. When I started at Comp, our surface finish spec was 12 to 24 RA. Well, that sounds okay, but RA is anybody that does cylinder bores can tell you, you can have a real peaky surface, a real valley surface, or a very random surface, and they'd all have the same RA. So RA is a lousy way of comparing most surfaces. With a camshaft, you really want a lot of load bearing area. So we started to work with the company and really start measuring our surface condition, doing the topology, the surface engineering at a different level. Worked a lot with Lake on this for his stuff, and Lord knows I measured everything you could imagine for him. We got in there and started to look at different systems to polish the camshafts. The first thing we did with MSC is we went from a steel hub CBN wheel to a carbon fiber hub CBN wheel. The second thing we did, we started changing the bond and the RPM and the infeed. Then we changed the dress. And eventually we started to go to a convex dress on our, a concave on the wheel, so it's convex on the cam. And it's only a few millionths of an inch, but now we have it set up where the camshaft surface on rollers is a few millionths bigger in the middle than on the sides. Then after doing that, we were able to bring our bearing areas at 20 micro inches, used to be on the order of, say, 30%. Those are up around 70% coming off the grinder now. And at 10 micro inches, we were able to more than double the effective bearing area at 10 micro inches. And basically, this is like wearing snowshoes. We were able to spread out the load in a way that you could never increase the strength that way with just material processes alone. People look at different cam grades. They look at 8620, 9310, 5150, 5160. All of those are in a very narrow range of strengths. The lowest of something you see might be 240 KSI. The highest you might see on a tool steel will be 300 KSI. The whole range is less than a 20% change. But when you can improve the surface finish on the camshaft and spread that load out, instead of making a 20% change, you can start making those 200% changes we're talking about. And what got me is when the guy who runs our dyno, he worked at this to the point where I can't bring him a camshaft back that hasn't been MSE. The camshaft's coming out after testing. We ran one intake manifold test. We probably had 300 or 400 pulls on the engine. He took the camshaft out, wiped it off with a rag, and sent it back to PRI with the salesman. You couldn't see any tracking in the lobe surface because the MSE had made the surface already conditioned and broken in, and it was spreading out the load. And when you see that load tracking, the wheel, you're thinking, oh, it's breaking in, it's doing good. But that tracking puts a real real stress riser on the edge of that track. So when you can see tracking, you're already starting an initiation point for a failure. So by going to the convex surface, going to the MSE camshaft, we made some tremendous improvements. It's been one of the coolest things I've ever been involved in, but it's been like a 10-year journey.
So, Billy, is MSC now available on all custom camshaft as an option?
It is. We used to do a belt polishing that we didn't talk a lot, and we replaced the belt with the MSE. The belts were really good, but the belts can actually add waviness to the profile and reduce some of that load bearing. The other problem we have with the belt is it's not random; it's very directional. Surface engineering, the guys in tribology would call it isotropic surfaces. When you go and do a centrifugal finish like we do this Kinetic Energy system, it's an isotropic finish, so you don't have all the scratches that you would have in a belt system.
So then if that works so well on the cam lobe, does that have implications that we should be looking at that on the rollers too?
The guys at the rollers were way, way ahead of us on this. When they horseshoe grind the rollers, the surface finish on the roller wheels were way higher than they were on the cams. If you look at a Jessel wheel, they actually grind theirs flat, and they have a multiple step process they run when they polish the roller wheel. to make the convex surface on it. It's a really cool deal that Danny did. And like one time they had one where their media wasn't right and a couple of camshafts failed. Like if that wheel if those edges of that wheel doesn't have that contour to it, it's really, really hard on the camshaft.
Chris Henderson on Facebook asked, is the MSC coating pink? And to my understanding, MSC is not a coating. It's a process by which you finish the lobe itself, right?
Right.
Yeah, Billy knows Chris. He's from Engine Masters, and you worked with him on his engine for quite a few years.
Oh yeah, no, it's not a coating at all. Generally, coatings in valve training are kind of a bad deal. They're too thin, they don't bond well, they trap heat in, and they flake off. Other than that, they're great. So,
sounds like an ex-girlfriend. Sorry.
So I'm pretty anti-coating, but DLC can get me excited because it's pretty amazing. But DLC only works in sliding. So like on lifter bodies, DLC is like the Mac Daddy. But usually camshafts and things like that, it's really hard to get coatings to work for.
When I hear DLC, all I can think of is dilithium crystals, Scotty. I need more of them.
She can't take much more.
Dahlquist is such a nerd. I love him.
Bewley, we need more power. Yeah.
I'm giving her all she's got, Captain. She can't take much more.
Beauty,
God, that went down a hole in a hurry, didn't it?
That was surprisingly good.
Who knew he could talk like that?
That was awesome. Bewley's got to do the angry Irish or Scottish guy later on. If it's not Scottish, it's crap.
You guys are never allowed to make fun of me for being a nerdy engineer anymore.
Nope.
Dude, listen, I'm 40. I grew up on TNG, okay? I hid from my father when I was a teenager upstairs with a quilt over the banister. My room was upstairs. I had no door. So if the TV was on, it shined down the stairwell, and he could see the light shining throughout the whole house. So I literally had to hang a quilt over the banister, over the stairwell, so I could watch TNG at 10:30 after the late show went off. It came on Saturday nights after, like, what was it, Saturday Night Live or whatever went off, whatever show that was. So, yeah.
I should explain that DLC is diamond-like carbon, just so that you don't think I'm completely dumb.
So you want to go into fine points of DLC 3 versus DLC 4?
Oh yeah, let's do that.
We're going deep now.
Yeah, I'm back to dilithium crystals there.
Oh man,
Which one would work better on rocker tips of an LS rocker?
A combination.
Oh boy.
So Billy, there was another question and I'm going to paraphrase this one on Facebook, but are there other things that are coming out that will enhance performance in this way that you guys are introducing right now?
We're always trying to push the envelope. And if I talked about anything that was, 6 months or a year out, my boss would probably choke me tomorrow morning. So, I'd really rather not get into anything. It's going to get me.
I'm not asking you to talk about futures or anything along those lines, or the words expressed on this podcast are not to represent future financial results for consumers or buyers of these products. No,
it really is one of those things that I joked about this to someplace, but when I tell people that I'm as excited about what's going on in our industry now as I ever have been, I'm being 100% truthful. There's so much technology going on. There's so many things that we're turning over that we didn't even look into before. There's these sweet accidents like the push rod and the dual conical spring, but there's so much of that that's going on that today that we may not know how good it's going to be for 5 or 10 years.
And I'll express this in my own terms, which is I've heard about DSC. It was all in the advertising. It said only available on cams for LS, and it was like, oh, great.
No, we can get that on. It's available on. It's available on any make of cam now.
Yeah, I wasn't able to sneak enough machinery into the building to do every camshaft is what happened. Since then, I've been sneaking more machinery in.
This is good. So when I ask that question about other things, I'm really asking about, are there technologies that have been in limited release that are now becoming more available on products that are shipping and orderable now?
I think what you're really seeing is right now the biggest thing that I see is a lot of the new camshafts are coming out with these new low profiles that John and I were playing with 5 years ago, but that stuff that we were playing with then is pretty much being used across the board now, and it's made really big improvements. You know, it's kind of nice when you go to cam shootouts and yours sticks out in a different way ballpark than other people's. And it's been a while for that. I had a good friend who sells sprint car motors, and he called me up the other day and he said, "Billy, this last cam you sent me, it got me a customer." He goes, "You've done me a lot of cool cams over the years, but I've never had a cam where I could swap an engine and it had the new cam in it." And the guy said he wanted to buy engines for me this season. So it's been really cool to see that.
I think that's wonderful. I can relate a slightly similar experience. I've been having my engine work done by Dugan's in Riverside, California, who run big engine programs for trophy trucks. And we adopted trophy truck technology to try and make drag week engines beginning back in 2006.
Super cool place to visit. Yeah.
Yeah, we've been pretty successful with that in terms of longevity and low profiles and valve train stability when we're doing 400 miles in a day pulling a trailer. And you guys have been the bomb, and working with those kind of shops has been the bomb. So I just wanted to say thank you personally. Guys, other questions for Billy?
I think we got them all, sir.
I just want to say thank you for pointing out that I was right about cathedral ports earlier in the show. Appreciate it.
You can send him $20, Billy, later on afterwards.
Yeah,
I just want to thank you for sticking around for 2 hours, man. That's crazy. I apologize for taking so long, but man, that was so interesting. We really appreciate it.
You don't understand, Billy. He would sit on here and bullshit with us for another 2 if we just didn't up and in the show. And he could stay here all night.
I was going to say, tell him to hang out for at least a few more minutes after I wind it down here in a minute, because it always gets more interesting after we go off the air. But
yeah, it's going to be funny with everybody trying to figure out why I said that Billy proved my point about cathedral ports. That's going to be fun.
Right. So anybody else?
That'll be an interesting talking point coming up this week.
I think Billy already knows this, but for John and Billy and all the people thinking about Jupiter, by the way, the atmospheric pressure on the surface of Jupiter is a little bit more than 1,000 bar, just to put that in context. So for all you guys trying to take it to Jupiter, just bear that in mind. You're going to need a bigger sensor.
Get a better map sensor.
So
14,700
PSI.
Yeah.
All right.
Exactly.
I'm going to fade you guys out.
Bill, right. I told you were going to love the Jupiter story.
And I did, and I have, and I will continue to. Thank you.
All right, gentlemen. Thank you, guys. Mr. Godbold, we really appreciate having you tonight. Thanks for coming on. We'll put this one up in podcast format in the next hour or two, and thank you so much. I'll have a link that your fans and friends can listen to and get educated. But thanks so much for joining us tonight. We really appreciate it. You're a trooper.
No, thank you for having us on. I really enjoyed it.
Thank you, Billy.
Thanks. Stick around.